Yep, now I can see that we are being recorded. Great. So it's my pleasure to introduce the speaker at our seminar today. So today we have Eva Bednarczuk from Warsaw, Poland. And she obviously represents the famous Polish School of Mathematics, one of the most advanced schools, at least very, very strong traditions going back at least into 19th century, possibly much further than that. So Eva was a student, as far as I know, of Stefan Ralevich. And I don't know the whole line, but I believe there are some connections with Stefan Banach, if I'm not wrong. So indeed, the Polish school it's a miracle, of course. So we have the representative of this miraculous school at our seminar. I've known Eva for more than 20 years. We produced a couple of papers in the past. I visited Warsaw many, many times. Eva also visited us here in Australia. I hope that we will have more chances to meet here and there. Probably I will stop my historical notes and memories and pass to Eva. She's going to talk about something related to abstract convexity, duality in non-convex minimization problems. I noticed in the abstract that Eva is going to talk about Phi-convexity and stuff like that. The concepts, as far as I can remember, were introduced in Poland. And in fact, the whole topic of abstract convexity is somehow related to Polish mathematicians. So it's great that Eva is continuing this history. So please, Eva, continue with your overview of recent results, please.
Thank you, Sasha, very much for the excellent and beautiful introduction. And it is my great pleasure to give a talk during this seminar, this particular seminar or webinar, like we are calling this right now. Well, for many reasons, because this is always great to be among colleagues, among friends, among people whom we know very well, and also to have the opportunity to see many new faces here. And well, the main reason, the second reason is that, of course, this topic which I am going to speak about is also investigated in the Australian universities very much. It goes back to Alex Rubinov, who I think is one of the founders of abstract convexity. So this is another important motivation. And last but not least, still the topic is very much alive and very much investigated right now by many people. Also by Sasha himself, but not only this, by Hoa, by David Yost, but Regina, I think she contributed a lot to this topic. So these are I think the strong motivation and a great pleasure to speak about this. Speaking about Polish mathematical schools, in fact, this chain is not that long. I am PhD student of Stefan Rolewicz, and Stefan Rolewicz was a student of Stanisław Mazur. So that the direct link to Polish mathematical schools. Now we are trying to do some genealogical investigations at Warsaw University of Technology. So if you visit the web page of our faculty, you can find there a lot of genealogical graphs, so to say, to study these sort of things. Yes, that's more or less what I would like to say before starting before starting mathematics. And well, as it's already mentioned, I would like to speak about the duality. Of course, there is a huge number of papers devoted to the topic. That's what I must say. But abstract convexity is present not that often, mainly, as I already mentioned, in the paper by Alex Rubinov himself, also Jon Borwein a bit, and Regina in the past. And now it is continued with a young researcher who joined the topic, like in Australia. In Warsaw, we also try to do this, mainly in connection with some algorithmic things. I will not speak about algorithmic consequences of these duality considerations. In fact, now we have a few, two young students. I think they are both with us today, who are working already on these algorithmic issues related to abstract convexity. So it is, we hope it will be fruitful to apply abstract convexity also in the construction of some algorithms. And well, the basic framework is the duality theory. Okay, that's what is our plan for today. I will start with some introduction, which will refer to the convex case, to the convex things. Next, I recall what is abstract convexity and especially Phi-convexity. And next, I will speak about dualities. And here you see there are 2 points. First is Lagrange duality, and second is Lagrange and conjugate dualities. So this suggests maybe that I will consider 2 different Lagrangian. So first of all, I propose some not propose, but well, just discuss a bit the Lagrange duality. And secondly, I change the Lagrangian and discuss the Lagrange and conjugate dualities. And in this second case, Lagrange and conjugate dualities will be strongly related. And the main topic I will discuss is zero duality gap. Okay, that's the idea. Yes. Yes, the approach I present here is based on the concept of perturbation function. The concept of perturbation function, that the classical approach, going back to, I think, Rockefeller, as far as I remember, and well, our problem P, which is our original problem, is the problem of minimizing over the whole space. Here, essentially, we can work in Banach space or in locally convex space, if you like. So our original problem is minimizing the over the whole space the function p x 0. Okay, so instead of writing f of x here, yes, f of x, and f of x could be any kind of function. So the sum of function, the composition, whatever you like. We, instead of this, we are writing just minimizing p of x 0. This means that this function p is essentially defined on the Cartesian product, and depends upon upon the space capital Y, which is not related directly to the minimization problem. This is the question of choice. This is the question of choice. So we can embed our problem P into different functions, into different perturbation function problems by choosing different spaces capital Y. That's the classical approach. And well, the convex case is the conjugate dual is to maximize. This is the topological dual Y star over the whole space Y star of minus conjugate of the perturbation function at the point 0 Y star. Okay, that I think is a classical thing. In convex case, everything is clear. Especially we know what is the perturbation function. Sorry, what is the conjugate function? The conjugate function for the function defined on the Cartesian product of the spaces. That's the crucial point here, because in the case of convexity, this is very natural. This is very natural, and you can trace this approach in the monograph by Radubot, which is one of his monographs, the one devoted to conjugate duality in convex optimization. Also in a very nice book by Constantin Zalinescu, who is working in locally convex space in principle, so in much general setting. That the conjugate duality. Okay, let me just make another approach. Another approach is through Lagrangian. So the Lagrange function is oh, sorry, maybe here is better to use this x. Also on the Cartesian product, x times the conjugate of y, and this is just a classical approach. So we are minimizing, our primal problem is minimizing over the whole space. Oh, sorry, I don't know why the function supremum over the dual of the Lagrangian, and the dual is maximizing. So we change the order of maximization and the minimization, and the typical classical Lagrangian is this one. So again, it is expressed with the help of the perturbation function, the conjugate, but not to the perturbation function as a function defined on the Cartesian product, but we fix x and we have the conjugate, which is defined only on the topological dual. Okay, that's more or less the story. Let us make a little zoom on this approach. So let us take P let us take P, which is of this form. Okay, so the minimization problem which is behind is the problem of minimizing f of x plus g of a of x, yes, over all x belonging to x. This is minimize p of x0. Yes, this is our original problem. So let it be like this. Let us consider that f and g are both convex functions, maybe proper and lower semi-continuous as well. And capital A is a linear continuous operator. So we can calculate the conjugate very easily by the convex analysis concept. So this is the supremum over all x and y of this expression. So we can here the linear functional x star on x, y star on y, minus f of x minus g a of x plus y. Yes, that's by definition. But here we are using more or less intuitively, we are using some basic construction in the space, in the Cartesian product of the spaces. So and among other things, we are writing this. Which is the bilinear coupling in the Cartesian product of the space x and y, and the conjugate and the dual space is x star times y star. Yes, the basic construction, which by the way cannot be easily generalized to the case where instead of linear functionals and affine supporting functionals, we would like to consider something which is nonlinear. I will come back to this topic. So this is the first thing which is not easy to be generalized to abstract convexity. This is the first thing. And I will point out next in a moment. So we are calculating this conjugate in a very easy way. We are using also the fact that here we are dealing with a linear operator. Yes, because here we are using conjugate operator, and we can rewrite these 2-3 lines, and we are arriving to the form of the conjugate of the perturbation functions. And if somebody is interested in the conjugate duality, so here we recognize immediately this P star of 0 y star, which is the objective of the dual. Yes, and now if we are looking at these several lines and we think about generalization to abstract convexity. So first of all, maybe one more remark about this capital A, which is a linear continuous operator. And we see that in fact, it does not work well if instead of linear continuous operator, we would like to take something nonlinear. So composition of 2 nonlinear mappings. Okay, so that's the first thing. Another thing is this P star x sub x at y star, which is the function with the help of which the Lagrangian is defined. So X is fixed and we are supremizing over Y. And again, in the convex case, and here the convex case means mainly that this bilinear coupling is this. Yes, this is our main manifestation of convexity, I would say, in this context, that we can more or less freely move around this construction, and we arrive to what is written in blue. So this P star sub X at Y star is just given by this blue formula, and this gives us the formula for Lagrangian. So that's the situation, that the convex situation. Yes. And well, the fundamental issues. Here one more observation, which is not true in general. So as you see, everything here is really very simple. I do not go deeply into the important issues of zero duality gap. There is a huge number of papers devoted to this topic. So zero duality gap is essentially when the optimal value of the primal equals to the optimal value of the dual. The classical thing, and the strong duality. So zero duality gap plus the solvability of the dual. So much stronger property, and these are the fundamental things. I do not give here the references, but a number of papers devoted to this topic is really great. Okay, so that's the introduction. I mean the classical thing. So let us, remembering this, let us just recall very briefly the basic idea of phi convexity. So essentially, the idea is to replace this linear coupling defined by linear functionals by some other functions phi. Phi is capital Phi is a set of real valued functions, small phi, which is closed under adding a constant. Essentially, this is the only requirement which is helpful. So in the convex case, these will be affine functions. Okay, and well, the basic concept is the concept of phi-convex function, which is pointwise supremum of the functions small phi from the set capital Phi. And we consider pointwise supremum over all those functions for which minorizes our function f, phi less or equal than f. Yes, and we call this set of the function phi which are minorizing our function f as a support. I think this terminology goes back to Alex Rubinov. He is using this in his book also. Rolevich, I would say that here I should add also the name of Dithard Palashke. Oh, sorry. also Dithard Palashka, who wrote a book with Rolevich. Yes. That the basic construction, and here abstract convexity refers to this family of minorizing function. So we do not have essentially, in principle, an inequality like in the definition of a convex function. Yes, what is the behavior of the on the convex combination of points of the function f? Do we have some inequality or not? In principle, not. But basing on this concept, we can prove a lot of facts. So I think this is a very interesting idea. So the elements of the set capital Phi are called elementary functions, and we can localize somehow the concept. So we can define what does it mean that the function f is phi convex at a point, okay, in more or less similar way. Moreover to this, I will limit the attention to proper functions. So the function is proper if this support set is non-empty, and the domain is of the function f defined in the classical way is also non-empty. In this sense, if the support is empty, then the function which is constantly equal minus infinity is also considered to be phi convex in this sense. Yes, that the basic definition. Examples, and I think these are first of all phi convex. Okay, so we are considering these affine functionals. So by choosing this fine, we obtain all the class or proper convex and lower semi-continuous function defined on the space capital X. And this is a general result in really general spaces. And the class which is maybe not that commonly used, however very important, this is this phi LSC. Phi LSC is the class of the functions which contains this affine component, but also is a quadratic component minus a norm x square. Here essentially we can work also in normed spaces. In normed spaces, this does make sense, and I think the important fact which shows how large is the class of phi LSC convex function is the paper, the fact taken from the Rubinov book that f is phi LSC convex if and only if f is lower semi-continuous and minorized by a quadratic function. Okay, so here what we are doing, we are so this family is parameterized by this a, which is positive number. C is just any real number, and L is just a functional. Okay, so these are the examples. I think we can now speak about some other examples which are not that maybe not that easy to see from the definition, but this class encompasses as well. This is the motivation why this class is interesting from the point of view of some algorithms for non-convex problems, especially this class contains Prox-bounded functions defined by Poliquin and Rockefeller, weakly convex functions, which I think are defined by Jean-Philippe Vial. And well, these weakly convex functions, I think, are more and more popular among people who are dealing with some algorithms, because especially for instance, in image processing, there is a lot of problems where weakly convex functions appear. And these weakly convex functions were also investigated by Stefan Rolewicz. He called this function paraconvex function. So here there is the terminology is as it is. So in fact, for a single object, we have at least 3 terms, which are quite well coined in the literature. Rolewicz was using paraconvex function, and there is a paper by him, paraconvex analysis. So he intended, or he did a lot to establish a subdomain, so to say, subdomain of abstract convexity called paraconvex analysis. And these paraconvex functions were also called semi-convex. In the book by Canarsa about Hamilton-Jacobi, you can find the same concept called, the terminology is semi-convex. Here I have some more examples to, I'm sorry for this. This is really not nice, but for some technical problems, I was not able yesterday to make the slides, but anyway, this is a minimization problems where the function g is just closed convex, lower semi-continuous, convex and proper probably. And here is the composition of a convex function which with the function which is Lipschitz itself and has a Lipschitz gradient. And one can show that this function is LB weakly convex. Weakly convex here, if you look at some other definition, yes, if you look at some other definition, that a function is called weakly convex if the function f plus this quadratic term is convex. And this quadratic term is multiplied by some constant rho, and this is I think useful to reflect this rho in the terminology. So to say that f is rho weakly convex means that this half of rho appears in this formulation. Okay, so here there are some other examples. So this rho Lipschitz gradient is rho weakly convex. C2 smooth function is rho weakly convex exactly at the situation when the minimal eigenvalue of the Hessian is uniformly bounded by minus rho. Okay, that's the small maybe insight into the weak convexity, some arguments why this weak convexity, which is the subclass of phi LSC convexity, could be of some interest. Next, conjugation. Well, conjugation is again, this is the generalization of the classical definition of the conjugate function, where instead of linear functional, we put here our function small phi from the class capital Phi. Yes, that the definition together with the conjugate. Here we to indicate which class we are referring to. We put this into notation. Okay, and the second conjugate also instead of linear function, we put the function phi in the definition, and we maximize, we supremize over the all the set capital Phi. And one of the basic facts, the characterization of phi convexity with the help of the second conjugate. And together with this, we can show a Young inequality. So f of x plus f star capital Phi of x. Yes, is greater or equal than phi of x. And in some analogy to the classical Fenchel-Moreau theorem, we have here the following equivalence. So the equality holds in this Moreau-Young inequality if and only if phi is the phi subgradient of the function f. And here I recall the definition of phi subgradient. Again, this is in some sense, this is in full analogy to the convex analysis definition, where instead of the linear functional, we are using these functions small phi from our class capital Phi. Of course, the concepts are in some sense a very natural generalization of convex analytic things, but from the computational point of view, these concepts are not that friendly, that easy to use, at least not as easy as it is in the convex analysis. For instance, proximal operator, it's something which is, well, this is an open question. Is it possible to define the proximal operator, phi proximal operator? Yes, something which works like usual proximal operator from convex analysis plays a similar role. Okay, that the definition. And now a few words about I recall I call this I give a title standard Lagrangian. What is this standard Lagrangian? This standard Lagrangian, as I mentioned in the at the beginning of this talk, is defined with this this conjugate P sub x conjugate. Yes, P sub x. So this is the more or less classical or standard Lagrangian, if you like. And this kind of Lagrangian were investigated by many authors. I think by Rubinov himself, first of all, also by Jean-Paul Penot and Alex Rubinov in the joint paper, and more recently also by Regina Buracic and Rubinov for some specific classes of phi. And this is nothing new, but this is not, maybe I would stress this at this moment, this is not the Lagrangian which allows us to produce some equivalent conjugate dual. So with this Lagrangian dual, we cannot produce equivalent conjugate dual. In convex case, this is okay. In non-convex case, this is not okay. We need to consider some other Lagrangian to arrive to equivalent Lagrangian duality and conjugate duality. And here just we can again I mentioned that of particular interests are these phi LSC or xi LSC classes, which include some functions important for applications. So this phi and xi differs only by this, maybe here I should write xi, differs only by the space on which they are defined. As essentially, the general form. Oh, I'm sorry. Yes, the general form is the same. The general form is the same. Here, since our original problem corresponds to P of X and 0, so here the Lagrangian can be defined like this. And here at the same time, you see that at work, this observation, I think, made in the book by Rubinov, then that in these kind of considerations, we can neglect constants. Yes, we can neglect constants. So here we have C, here we have C. So this C cancels. So we obtain the same formula for the Lagrangian if instead of phi we take without this C. Yes, so we consider phi from the class. I call it phi LSC 0, which is the class of functions phi, which are in the form minus a norm x square plus linear Lx only, without a constant. Yes, so this is absolutely enough. Okay.
There seem to be too many zeros in 3.
Where?
Should be probably X, not 0. In the formula.
In this formula 3?
Yes.
No, that's okay.
Then where's X is only in PX? Okay.
Yes, yes. And zero duality gap. Here we are approaching zero duality gap through some minimax theorems, which are proved by my former PhD student Monika Syga in her PhD thesis. So she investigated minimax equality in general and also in the context of of the Lagrangian. This can be rewritten in the case of the Lagrangian. So what we see here, this is if and only if the equivalence of this is zero. This point 2 is the zero duality gap. And this one I is what is called intersection property, due to the fact that in fact here we have this condition that the intersection of some sets should be empty. And well, for every alpha which is less than infimum supremum, there exists Xi1, Xi2 from this class Xi LSC, and Phi1 and Phi2 from this support set, such that this intersection is empty. This condition, I think, is crucial, and well, some people maybe not feel very comfortable with this condition, because this does not remind us any other conditions we know about zero duality gap. But the advantage here, what is the situation? The situation is in fact that this theorem can be proved for any class Phi and Xi. And when applied to our classes Phi LSC, Xi LSC, it says if we recall what is the form of Phi1 and Phi2 in the class Phi LSC, so in fact this condition, the consequence of this condition is that Phi1 and Phi2 need not contain a quadratic term, because otherwise this intersection is non-empty. Okay, so this is one of the consequences of this intersection property. And this property, I think, what we are trying to do is to rephrase somehow the intersection property to understand, to express it in terms which are more familiar, I mean appear more often in the context of zero duality gap for optimization problem. Okay, let us start now to the as I mentioned before, we have this infimum, we have this relation that the infimum of P star X is equal to minus P star at 0 Y star, which is not the case, for general Phi convexity. Okay, so first thing which we need to do is to define what does it mean, the conjugate for the function which is defined on the Cartesian product. Sorry. Okay, so let us fix our attention at the function, at the conjugate function P x and y of the form f of x plus g x plus y. This is in some sense the simple case. What could be done also is to compose G with a linear operator, like at the beginning of our presentation when I was talking about convex case. And let us assume that f of x and g of x are Phi-convex and Xi-convex. Okay, so these Phi and Xi are essentially different sets of elementary functions. And let us, what we need to define the conjugate. To define the conjugate, we need to define this coupling function on the Cartesian product. Okay, and here is some idea, how can we define this in the case of the Cartesian product capital Phi times capital Xi. This is this CPL definition. If of course Xi is just a linear thing, we obtain the classical coupling on the Cartesian product. So here, this is just an idea. I will show you how it works, but essentially, this is one of the first concepts along this line. Not much can be found in the literature, at least not in the context of duality. In the context of duality, I was not able to find any other idea. How can we define the coupling on the Cartesian product? Okay, so with this, we can again, we can cancel this constant. It is enough to use the part of the definition when the of the function Xi when where the constant is 0. And in fact, of course, when Phi and Xi are both linear, this is standard bilinear coupling in the Cartesian product. Okay, so now how it works? In the context of our perturbation function. Well, now C sub C means that we are using this coupling C. This coupling C, as I mentioned, is well, it's one of the possibility. Let us put it in this way, and we will see how it works. So this is by definition. This is this Phi of x plus Xi x plus y minus Xi of x minus P x and y, and again, this conjugate function P star is can be expressed like this. So this is supremum over all x, Phi of x minus f of x minus Xi of x. This is under supremum. And this is the conjugate of G. Yes, that's the conjugate. And well, now we see how it works. Yes, so the dual objective. The dual objective, we will consider several cases. So first of all, Xi and Phi are both equal. Means that f of x and the g of x are Phi-convex. Let us put it in this way. In the context of weakly convex means that both f of g are weakly convex, or both f and g are Phi LSC convex. And in this case, this objective function of the dual is like this. Again, the same formula here as before. But here, as you see, there is one problem, that here is this not f star but star f, which is the conjugate, the Phi conjugate of f, but at the argument minus xi. Essentially, it is not always so that minus xi belongs to our class capital Phi. So this is, for instance, the case in the class Phi LSC, that minus Phi is not a member of Phi. So here we need somehow to redefine or to stress this fact that this is in fact something a bit different. And now Lagrangian dual. I mentioned to you that Lagrangian dual, we need to change the Lagrangian to get the equivalent conjugate and Lagrangian dualities. And this is the new Lagrangian. This is the new Lagrangian. And you see, we obtain because this is Lagrangian dual objective. Yes, this is the infimum over all x of our Lagrangian. And we obtain that the equivalence, that the conjugate dual objective is the same as the Lagrangian dual objective. This is in the case xi is equal to Phi, the classes coincide. Here is the particular case when we consider these Phi LSC classes. And here this is important to pay attention to the fact that in fact minus function is not the element of the class whenever a given function is in the class. So here we can also calculate the conjugate, and here we always have this problem related to the fact that we are dealing with the class which is not symmetric in this sense. Okay, so the idea is that instead of the conjugate of f, we consider the conjugate of f tilde. F tilde is of this form, and this form is is the function we need to consider instead of f. Here we can rewrite this in this last line. We rewrite everything by identifying a function xi with just a and v. Yes, a and v. So we can put it in this way. This is the second case, and the Lagrangian objective is again the same, so this is not surprising. And well, here is the case which is maybe interesting from the point of view of application. This class, which needs to be symmetric, is a subclass of the class capital Phi. And this is, for instance, the case where we consider just affine functionals. Yes, this is a nice symmetric subclass of Phi LSC. So what does it mean? It means that one function is convex and the second function is Phi-convex. Okay, and then we arrive to the conjugate dual objective, which is just very nice. Here is conjugacy in terms of convex analysis. In terms of convex analysis, so xi is defined by this. Yes, this one. And the same for Lagrangian dual. And well, that's in fact the essential part of the talk. I would like to finish my my presentation with with some results referring to the zero duality gap, as maybe some of you know. There is quite a recent paper by Hoabui, Regina Buracic, Alex Kruger, and David Yost, devoted to the same topic, I would say, but they are approaching the conjugate duality just not through the perturbation function, but via infimal convolution. And with this approach, they provided the following theorem, the following characterization of zero duality gap. Here is epsilon's phi subgradient appears, and both function f and g are Phi-convex. So they consider only this case, which is, I think, the first one on my list, and this is the dual problem they are investigating. And along this line, we also trying to investigate the zero duality gap via minimax, because when we have the equivalence between conjugate duality and Lagrangian duality and some suitable Lagrange duality, then we can also investigate zero duality gap for conjugate duality via intersection property via minimax duality. So this is an alternative result, an alternative approach, I would say. And again, this intersection property appears here. This basic zero duality gap is written for any class capital Phi. Okay, so this I think is the last result I would like to present. Maybe there is one more thing that in fact we can show that this condition which appears which is with epsilon subgradient is a sufficient condition for the intersection property. But this, I think, these are quite recent results, and this probably needs to be investigated more closely, the relationship between these sufficient and necessary conditions for a zero duality gap. Thank you very much for your attention, and I finish my presentation. Thank you.
Thank you, Eva, very much. Interesting presentation, beautiful formulas. And it looks like you've clarified a few things related to those phi convexities. Any questions, comments from the audience?
Hi, it's Hua here. I have a question regarding to the theorem that you cite in our paper with Alex.
Yes.
Yeah.
The previous slide.
So I think it's not really our result actually is slightly different. It is not that f and g are Phi-convex. So our condition is that f and g are any function, and yeah, it's not necessary to be Phi-convex. It's any functions, and the phi here is not only the condition that zero belongs to the set. We also have the condition that it has to close under the addition operator as well. So it's a little bit different. The theorem is not like this one. It's just a common.
So you mean this is not exactly what you are using?
Yes. So our theorem is f and g are not necessarily is any function or any functions, and not necessarily to phi convex. And the condition on the set phi here is not only 0 belong to phi, but also the addition operator closed in this set as well, which means that if phi 1 and phi 2 belong to that set, then phi 1 plus phi 2 belong to that set as well. So there are two conditions.
So as Eva said, this issue requires probably more investigations and the close.
Yeah, but the assumption on f and g are minor because we don't. This is for any functions.
This is for
yes. This is a big difference. Yes.
Yeah, it's a big difference.
Yes. Yes. Yes.
Okay.
Okay.
More comments, questions?
Yeah, I think I'm not really familiar with the intersection, but I think it's quite interesting with that property. So in standard convex analysis, is there any similar result on standard case?
Yes. Yes, I did not present here how it works in convex case. We have done it in some paper, I think. So there are some. Yes. That's an important question because people would like always to know how it works in convex case.
Because I remember Regina told me that the necessary and sufficient conditions for zero duality gap in standard convex cases yet no still. So I think if your intersection property easily apply for standard convex cases would be very valuable. I mean, up until now, there are some conditions, sufficient and necessary conditions, but before there's no property.
Yes, and as you see, the property is, I would say this is purely algebraic. Maybe there are some connection with weak star topology, but we are still investigating. We are still investigating this, and it would be really nice to establish some relationships between the two, for instance, and also with some, because, for instance, in the case of phi LSC, if the class is here not phi but phi LSC, then this intersection property simplifies considerably.
Okay, thank you. So indeed, it would be good to clarify the relationship between, in a sense, primal space conditions and dual space conditions.
I mean, I just have an additional question for you. So is that condition I look like primal condition, not dual condition? I mean, yeah, of course, for Lagrangian function, which seem like primal condition and dual. I think
it is questionable what to call primal, what to call dual. That's why I carefully said like primal, like dual, subdifferential. Yeah, this is a natural question, and of course there must be connections between the two approaches, two sets of conditions, and normally primal space conditions are weaker. And this is what Eva demonstrated in this talk. Maybe not precisely the result cited from our joint paper, but the idea, I think, is still.
Idea is yes. Oh, I'm sorry. I will check this. Maybe there is some. Okay.
And then some new theory will emerge. Okay,
Yeah.
more questions, comments, suggestions. I don't see any raised hands. So thank you once again, Eva, for a very nice presentation. Thank you for joining us at this seminar. Thank you everybody for coming to this webinar. And please come again next week.
Oh, yes, with pleasure. Thank you. Thank you very much once again for your attention. Thank you for your comments. Sorry for this imprecision about the theorem. I will check it again. But well, the relationship, I think, between the two conditions, I think, is proved based on the right formulation. So thank you.
This proves usefulness of our seminars.
Yeah, yeah. Thank you. Thank you so much.
Thank
Okay.
you.
Thank you, everybody. And the meeting is closed. Have a great evening or have a good day for Europeans.
Thank you.